Okay, so we are going to look at anti-differentiation, which we already introduced in the last chapter, but now we are going to take it a step further. So this is just a review of the indefinite integrals, the power formulas, with the exception of to the -1, natural log, absolute value, our trig formulas. And again, you'll notice all of these have plus c because they're indefinite. We do not have bounds. And then we have exponential and logarithmic, and all we really need to know is e to the u. So what we're going to look at in this section is compositions. So we know the antiderivative of cosine is sine, but what about the antiderivative of cosine of 2x? This is not equal to sine of 2x plus c. Okay, no, we can't do that. Because, think about that. If that were the case, remember when we want to check if we did the antiderivative correctly, we do the derivative of this. So if we did the derivative of this, we'd get cosine of 2x. Oh, but we'd have to multiply by 2, and then the plus c would be a plus 0. But that's not what we started with, right? There's a 2 that's missing. So this is where we have to do some substitution. So here's substitution method. This is the chain rule in reverse. So basically, we have a function f of u of x, and then you'll notice here it says u prime of x dx. So when we take the antiderivative, we're just left with the antiderivative of this with the inside part. And I know that looks really confusing, so I'm going to take you through some examples step by step. Okay. So first thing, we have this idea of having u. U is generally what we want to think of as the inside. Now, in the first few examples, u will be given. So I'm going to walk you, this one's already done for us. So first thing we want to do, we have 4 here, and then we have 4x minus 5 to the 6. This is going to be u. That's our inside part. So u is 4x minus 5. So next thing we want to do is find the differential du. Now we did differentials just a little bit in the last lesson. This is where we want to move, think of du dx. Well, if u is 4x minus 5, then it would be 4. And then we just want to move the dx to the right side, so it looks like that. Now, the next step, we're going to rearrange and rewrite the integral in terms of u. Okay, so you should no longer have the original variable. So here, if you notice I have a 4 and a dx, well 4 dx was equivalent to du. So if I just move this over, right here I get the 4 dx, I can replace that with du. The 4x minus 5, well that's u. Remember, that's what we originally let u equal to. So I have u to the 6th power. Now, what's nice about this is now that we have the same variable in the integrand, right, and as part of our differential, we can integrate this with respect to u. So u to the 6th becomes u to the 7th over 7 plus c. We don't want to leave it with respect to u. We want to substitute the original value back in, variable back in. So here, u was equivalent to 4x minus 5, so to the 7th over 7 plus c. Okay, so let's try a couple of these where we're provided with u. So the inside part, that's x minus 7. So du is just equal to 1 dx. So now I'm going to replace my variables. So this becomes, instead of x minus 7, that's u to the 3rd power, and dx is equivalent to du, so I'm just going to put du. So we take the antiderivative, that's u to the 4th over 4 plus c, and that Now we're just going to replace u again. So we have x minus 7 to the 4th over 4 plus c. Again, I'm not going to walk you through the process of confirming your answer, but you can do the derivative of what you end up with to make sure you get what you started with. Next one, this time I'm given u is x squared plus 1. So du is 2x dx, which is really nice because 2x and dx, if I combine those, that's my du, right? So I'm just going to rearrange. This step is completely optional, it just helps so you can kind of see where I'm replacing all the x's with u's. So this piece, well, that's going to be the square root of u, and this piece is du. So the integral, I'm going to write this as u to the 1/2 du. So now I have u to the 3/2 over 3/2, which is multiplied by 2/3, plus c. And so now we replace, so it's 2/3 x squared plus 1 to the 3/2 plus c. Let's try another one. Here, u, the inside part, is x squared plus 9. So du is 2x dx. Again, works out really nicely because 2x dx is right there. So I combine those, that's my du. And the x squared plus 9, that's u to the 5th du. So when I integrate, I get u to the 6 over 6 plus c, which becomes x squared plus 9 to the 6 over 6 plus c. All right, next one. This one gets a little more confusing. So when we have e to a power, the power we think of as the inside part. So I'm going to let u equal cosine x. So du is negative sine x dx. Here's where it gets a little more complicated because I have a sine x and I have a dx, but I don't have a negative sign. So this is where what we say, we kind of compensate for that. So I'm going to multiply both sides by -1. In other words, negative du is equal to sine x dx. So think about that for a minute. If I just rearrange this, make this sine x dx right next to each other, this gets replaced with a negative du. So I have e to the u, right, cosine is u, with a negative du. The thing is, though, that negative in front of the du, it's much easier if we think of it as a coefficient. It's not subtraction, it is a -1. So I'm just going to move that -1 to the front of the whole thing. Coefficients can always be brought out in front of the integral. So whenever I get a coefficient in front of the du, I automatically move it in front of the integral. So now I just integrate e to the u. Well, that's e to the u, so it's the negative and then e to the u plus c. So our final answer is negative e to the cosine of x plus c. All right, e. Now I have u is 5 plus 2x cubed. So du is 6x squared dx. Now I look back at my original problem. I have an x squared and I have a dx. But over here I have a 6x squared dx. So I see I have an x squared dx, but I don't have a 6. So what I'm going to have to do is I'm going to have to divide by 6. Or think of that as multiplying by 1/6. So 1/6 du equals x squared dx. So it's almost like whatever I'm missing, that's what I have to divide by or multiply by the reciprocal. So now these two parts combined, x squared dx, is equivalent to a 1/6 du. Now remember what I said about the coefficient. It's easy to just move that 1/6 out to the front. So now I have square root of u, or u to the 1/2 du. Again, I'm replacing all of my x's with u. Now I'm going to integrate. So u to the 1/2 becomes u to the 3/2 over 3/2, which is multiplied by 2/3, plus c. Now I can simplify this, so that becomes 1/9, and u is 5 plus 2x cubed to the 3/2, and then plus c. Okay, so the next few examples, I'm not going to give you u. We have to figure out what that is. So the first one's pretty straightforward. It's going to be whatever's inside the parentheses here. So I'm going to make that u equals 4x plus 3. So now I'm going to find du, which is 4 dx. Now, you'll notice I don't have a 4, I just have a dx here. So I'm going to divide both sides by 4, or think of that as 1/4 du is equivalent to dx. So I'm going to replace that 1/4 du. So I'm going to put a 1/4 out in front, integral, right, du. Well, what's inside? 4x plus 3, so that's u to the 4th. Now I can integrate. So I have u to the 5th over 5 plus c. So my final answer is 4x plus 3 to the 5th over 20 plus c. Okay, next one is a little more tricky, but if I just think of ln to the 6th of x is ln of x to the 6th, I'm going to let u equal ln, because that's my composition. And then I get 1 du is equal to 1 over x dx, which I have right there. So I'm going to rewrite this as u to the 6th du. So I get u to the 7th over 7 plus c, which is going to be ln to the 7th over 7 plus c. Next one, all right, since I'm not going to make it let equal to x, I'm going to let u equal x squared plus 3. So when I do du, I get 2x dx. Well, here I have an x and a dx, but I don't have a 2. So I'm going to multiply both sides by 1/2, and therefore I'm going to replace x dx with 1/2 du. So I have a 1/2 out in front, du, and then I have 1 over square root of u. Right? Well, that's really u to the negative 1/2. So when I integrate that, I get u to the positive 1/2 over 1/2, which is really multiplied by 2. So you'll see those coefficients cancel. So I just get square root of x squared plus 3 plus c at the end. Next one, I have two sets of parentheses. I'm going to use the one that has the exponent. So I'm going to let u equal x cubed plus x. So du is 3x squared plus 1 dx, which is very convenient because I noticed those two parts combined. That's my du. So this one I just have u squared du. So I'll get u to the 3rd over 3 plus c. So x cubed plus x to the 3rd over 3 plus c. Okay, using substitution with a trig identity to evaluate each integral. So I have cosine to the third of x. So what I want to first do is I'm going to rewrite this as cosine of x times cosine squared of x. Now, in order to integrate sine or cosine, we want to have sine or cosine within the integrand. And so what we want to do is we want to replace either cosine or cosine squared with something with sine x. You may remember sine squared plus cosine squared equals 1. So I actually can replace cosine squared with 1 minus sine squared. So now what am I going to make my u equal to? I'm going to let u equal sine of x, because that's the part that's getting squared. So now du is cosine of x dx, which I happen to have here. So now I'm going to rewrite this. So it's 1 minus u squared and then du. So it becomes u minus u cubed over 3 plus c. And then we go back and substitute everything in. So sine x minus sine cubed x over 3 plus c. Okay, so next we want to look at changing the variables for definite integrals. So what happens if we have bounds? Well, what we're going to do is we're going to change those bounds to reflect u. So you'll see here it went from a to b, and then we change it to u of a to u of b. Okay, so our example, we want to make u equal to x squared minus 4. So du is 2x dx. Now I see I have an x and a dx, not a 2, so I'm going to keep in mind that 1/2 du is x dx. So I basically have 1/2 out in front, and then I have a 1 over u and a du. But I don't want to use the bounds of 0 and 1 because 0 and 1 reflect the variable x. So we go back to here where we had u is equal to x squared minus 4. And we want to have u of 0. So I plug in 0, I get negative 4. So where 0 was, I'm going to replace that bound with a negative 4. Next, I have u of 1. So I plug 1 into x squared minus 4 and I get negative 3. That means my new upper bound is negative 3. Now I'm going to integrate with respect to u. So I have 1/2 ln of absolute value of u. And we want to evaluate this. Actually, I'm going to put from negative 4 to negative 3. Now what's nice about this, I don't have to go back and plug in x because I changed the bounds to reflect u, so now I can just plug right into u. So I have ln, absolute value of negative 3 would be 3, minus ln, absolute value of negative 4 would be 4. So I have 1/2 ln of 3/4. Here. Okay, so this one's a little tricky. This one I'm not going to make u equal to secant squared. I'm actually going to make u equal to tangent. The reason is sometimes when we're doing u substitution, it's helpful to make u equal to whatever derivative you see in the integrand. And we know that the derivative of tangent is secant squared. So right here, I see that's my du. Now I'm going to change the bounds at the same time. So u of 0, so tangent of 0 is 0. And then u of pi over 3, so tangent of pi over 3, so that's going to be sine of pi over 3 over cosine of pi over 3, so that gives us root 3. Now I'm going to rewrite this. My bounds are now from 0 to root 3, and then I just have u du. So I get u squared over 2 evaluated from 0 to root 3. So I have root 3 squared over 2, which gives us 3/2.